All right, welcome everybody to the one of the last topics of the class, and that's elliptic curve Diffie-Hellman. So let's dive right in. We're going to talk about how do we sort of generalize this idea of the Diffie-Hellman key exchange to elliptic curves. And as a reminder, the Diffie-Hellman key exchange, really all you need is a cyclic group to have the Diffie-Hellman key exchange, because the Diffie-Hellman key exchange is based on the idea that the discrete logarithm problem is hard to solve for some cyclic groups. Okay. Announcements. Again, make sure you're working on everything in MyOpenMath. You've got lots of stuff that you can be doing. And then Dr. Hassinian's office hours. Dr. Hassinian's graciously agreed to cover for me the rest of the semester. So her office hours are Tuesdays 10 a.m. to 1 p.m., Thursdays 11 a.m. to 12 p.m., and she's also in the MEC on Thursdays from 10 a.m. to 11 a.m. She will also be there in class for giving, for time for you guys to come in and take quizzes or work on projects and to ask her questions. So she, again, class is flipped the rest of the semester. Watch these videos, come into class during the regularly scheduled time, and she'll be there to help out with any questions that you have on homework, quizzes, projects, etc. Okay, so that's that. All right, so we want to talk about the elliptic curve Diffie-Hellman key exchange. Okay, so given an elliptic curve E, which is y squared equals x cubed plus ax plus b, where again a and b satisfy that 4a cubed plus 27b squared is not equal to 0. That's an elliptic curve. We're going to call E of fp, that's the points xy with x and y in fp that satisfy this equation, but mod p. Okay, so that's the elliptic curve over the finite field fp. Okay, and for a lot of choices of p and a and b, it happens to be the case that E of fp is generated by a single point capital P. So capital P has nothing to do necessarily with little p. It's just I'm using capital P for point and little p for prime. Okay. So for a lot of choices of P and A and B, there is a single generator of the whole group EFP, again, with that group being the group under that weird addition operation that we defined in the previous lectures. Okay, so it happens to be the case that every point in E of fp is of the form m times this generator for some integer m. Okay, so in other words, E of fp is a cyclic group in those situations, and in those cyclic groups, the discrete logarithm problem is extremely difficult to solve. It's why, again, a lot of modern, if you look at any website at random that is encrypted, so that begins with HTTPS, most of them use elliptic curve cryptography because it's just more secure for smaller prime numbers p. Okay. Than equivalent security for RSA or for Elgamal, for instance. Okay, so let's talk about the discrete logarithm problem really quick. The discrete logarithm problem, as a reminder, in any cyclic group, the discrete logarithm problem for any cyclic group is given a generator G of the cyclic group G, capital G, solve the, really quick, and H, some element of the cyclic group capital G, solve G to the X equals H. Right, that's the discrete logarithm problem. I don't know why I put an S there. This is the LP, discrete logarithm problem, for any cyclic group with a generator G. Now, in some cyclic groups, the discrete logarithm problem is really easy to solve. In the group of integers mod P under addition, the discrete logarithm problem is so easy to solve. You just divide both sides by g to figure out what x is. Now, when I say divide, I really mean multiply by the multiplicative inverse of g. But still, the discrete logarithm problem in that setting is incredibly easy to solve. But as we saw, the discrete logarithm problem for, say, fp, the field of integers mod p under multiplication, the discrete logarithm problem there is incredibly difficult to solve, and that's what the Elgamal encryption is based on, is that problem is incredibly difficult to solve for large prime numbers p. Okay, it turns out that the discrete logarithm problem is even more difficult to solve for elliptic curves. Okay, so given a generator P of E of Fp, so that's acting like G up here, and another point Q in E of Fp, we want to try and solve the equation X times P. So again, that's going back to the operations we talked about last time. Think about 2 times P. You had to find that slope M was 3 times x1 squared plus a divided by 2 times y1. And then you find x3 was m squared minus x1 times 2. And then y3 is y1 plus m times x3 minus x1. And then the resulting point is x3 minus y3, right? Really weird, really tough, and that's why solving, and that's just for 2 times p. If you want to do 3 times p, you have to do 2 times p plus another p, and then so on and so on and so on. Okay, so it's a nightmare. It's a nightmare to try to even just add a point to itself by hand. Sage can do it quickly. So trying to undo that, trying to figure out, I have some multiple of p and it equals this point. What is the multiple that I'm looking at? That's why this is so difficult to solve this equation here. And that's what leads to elliptic curve cryptography being really secure. Okay, so the difficulty of the discrete logarithm problem for elliptic curves over the finite field Fp, that leads to the elliptic curve version of the Diffie-Hellman key exchange. Okay, so we're going to talk about how can Alice and Bob, they want to communicate, they want to arrive at a shared secret key for use with encryption somehow. How can they use the Diffie-Hellman key exchange in this elliptic curve setting? Okay. All right. So Alice and Bob want to arrive at a shared secret key using the elliptic curve E, which is y squared equals x cubed plus ax plus b. At this point, I should mention there are some modern elliptic curves that actually don't look like this form. They're written in a slightly different form. And this is just to make the curve simpler to look at. The number is a little bit nicer. But ultimately, every elliptic curve you can rewrite in this form by changing variables. Okay, and I'll mention that later on. So they agree publicly to a prime number, little p, and a generator, capital P, of the elliptic curve E of Fp. Again, all of that information is communicated publicly. And in fact, in modern cryptography, there's only a handful of elliptic curves that most people use in practice. So they can say, go and use curved. There's a curve that's typically used for the Diffie-Hellman key exchange called curve 25519. They say, hey, go use curve 25519. And when they look that up, that actually tells them the A and B values and the prime number P to use with that curve and the generator to use. Okay, so this is all public information that they're either, figuring out and communicating with each other about, or more likely they're going and they're looking this information up from a website or from the National Institute for Standards and Technology, NIST, and using information that they get from there. Okay, so they agree publicly to the prime number P and a generator, capital P, of the elliptic curve over the finite field Fp. Okay, and then Diffie-Hellman goes in exactly the same way as it did before. Right? Alice takes the generator and multiplies by her secret number that we're calling capital A, because I'm using little a right here. So that's why I'm not using little a. But Alice comes up with a secret key capital A, and that's just a number. It's her number that she's going to multiply the generator by. Just like with the Diffie-Hellman key exchange before, we took the generator to her secret key. That was because the operation there was multiplication, and so the field was generated by G to the stuff. Now the field here is generated by just multiples of the base point, the generator. Okay, so she's going to choose a secret key, capital A, and Bob does as well. He chooses a secret key, capital B, and Alice computes, obviously in this elliptic curve setting, capital A, her secret number, times P. Okay, this gives her another point in the elliptic field over FP. Okay, and then she sends that point to Bob. She says, my point that I got when I took my secret number times the base point was this this point Q. Bob does the only thing he can do. He computes B times P. We'll call that capital R, and then he sends that point to Alice publicly. Okay. Now the question is, what secret key can they both arrive at easily that an eavesdropper can't arrive at? So Alice can compute. So Alice receives R, which is B times P. So what can she do? She computes the only thing she knows how to do. Just multiply this this point by A, her secret number. So she computes A times R, which is the same thing as A times B times P. And because, I didn't prove this, you have to kind of take my word for it, but because the points on an elliptic curve under this operation of addition is a group, this is the same thing as A times B, just as integers times that base point P. Okay, so Alice can arrive at the point A times B, which is a number, and then take that times the point P in the elliptic curve. What does Bob do? Bob receives from Alice Q, which he knows is A times P. So what does he do? Bob computes the only thing he knows how to do. B times the point that he got, B times Q. But that's B times A times P. And again, because this is a group, this is the same thing as B times A as numbers, but B times A is the same thing as A times B, and then times the point. So they can arrive at the shared secret key, A times B times the point P. And Alice, if Alice is listening in on any of this, if an eavesdropper is listening in on any of this, an eavesdropper, from just knowing Q, it's really, really difficult to work out what A was. And from just knowing R, it's really, really difficult to work out what B was, right? So an eavesdropper can take this Q and this R and try to figure out A and B, but it's going to take forever to do that if P is a relatively big prime number. Okay. And so that's the Diffie-Hellman key exchange. The shared secret key is actually a point in E of FP. It's A times B times the point P. Okay. Alice and Bob can both arrive at that using only their secret information and then the publicly agreed upon information that they discuss ahead of time. All right, so let's do an example. We're going to use small numbers here, and then in the next example, I'll show you some numbers that are used with modern cryptography, and the numbers are pretty big. However, when compared to the numbers that have to be used with RSA to achieve the same security, they're actually pretty small. Okay, so let's say Alice and Bob want to arrive at a shared secret key. They agree to use the elliptic curve E, which is y squared equals x cubed plus 3x plus 5, with the prime number P equals 31. They choose the generator P, which is the point 1430 in E of F31. Let me close that parentheses there. Alice chooses a secret number 19 and Bob chooses 27. What point does Alice send to Bob? So I would encourage you, do this in Sage. I would encourage you to pause the video and try to figure out what point does Alice send to Bob, then figure out what point does Bob send to Alice, and then compute the shared secret key from both their perspectives to make sure they arrive at the same thing. Okay, so pause the video, go open Sage, which is sagemath. sagecell.sagemath.org. And in fact, here I can pull that up there. There's the website that you can do this stuff in. Try and remember some of the operations we were doing and some of the code that we used, or look back at the previous video. But try and compute, what point does Alice send to Bob? What point does Bob send to Alice? And then what's the shared secret key? Okay. So switching back to the notes, I'm going to write out what Alice sends to Bob. Alice is going to send to Bob the point Q, which is A times P. So that's the point 19 times 14, 30 in this elliptic field. By the way, elliptic curve over this finite field. If you also want to check, is this a generator? You can do that. You can check, is this elliptic curve legitimate by checking is 4a cubed plus 27b squared, is that not equal to 0, mod 31. You can check all those things, or you can trust me that they're true. Okay. So Alice sends to Bob this point, 19 times the point 430, which is not just 19 times 14, 19 times 30. If that was the case, then this would be really pointless. It would be very easy to undo these things. Okay. So we'll compute that in a second. Bob computes the point R, which is B times P, which is 27. I think 27 times, 27 times the point 14, 30. Okay, so let's go compute those things. So in this sagecell.sagemath.org, I give myself my elliptic curve. E is the elliptic curve over the field F31. So I type GF31. And then with the coefficients 3 and 5. That's A and B. Okay. P is the point on the elliptic curve 14, 30. And Alice computes Q, which is, let me do A is 19 and B is 27. So Alice computes the point Q, which is A times P. Let's look at what that is. This is taking a second. I might need to refresh this page. Let me refresh this page really quick and try again. There we go. And Alice gets the point 28, 0. So I'm just writing that down. That is what Alice gets, and that's what she sends to Bob. The point 28, 0. She sends that to Bob as well as the rest of the world. Everyone sees that point that she sends. Okay, Bob computes the point R equals B times P. Let's see what Bob sends to Alice. Bob sends the point 26, 19. I'm just writing that down as well. Okay. All right, so that's what Alice sends to Bob and Bob sends to Alice. Now, what is the shared secret key? From Alice's perspective, Alice receives the point R, so Alice computes A times R. So she computes 19 times the point 26, 19 in the elliptic field, the elliptic curve over the finite field F31. All right, so that's what Alice computes. Let's go and see what she gets. So Alice computes print A times R. Alice gets the point 28, 0. Oh, that's scary. But that's fine. What does Bob compute? from Bob's perspective, so Alice got A times R was 28, 0. Bob computes so this is from Bob's perspective. Bob computes, well, he receives Q, and the only thing he can do then is compute B times Q, which is, 27 times 28, comma, 0. Okay, so let's go see what that is. Print B times Q. And Bob also gets 28, comma, 0. Wow. Which is, again, so that's actually the point that Alice sends to Bob. Alice kind of unintentionally sends the secret key, but there's no way for Eve to know that. There's no way for Eve to know that with what Alice sends to Bob and what Bob sends to Alice, that Alice actually technically sends the secret key to Bob. And so this is still considered a secure, even if you accidentally somehow send the secret key, it's still a secure way to send messages, because again, there's no way for Alice to know that. Or sorry, for Eve to know that. Okay. All right, so that's that. Now, let's talk about some numbers that are used in modern cryptography. Okay, let me switch back to the notes here. One commonly used, like I said, one thing that people can do when they're agreeing to use elliptic curve cryptography is they can use a commonly agreed upon, like safe elliptic curve. So one commonly agreed or one commonly used elliptic curve in modern cryptography is a curve known as NIST P256. And so that's the elliptic curve given by E is y squared equals x cubed minus 3x plus b, where b is a very, very, very big number. Okay. So I'll show you B in a second. I've got another Sage cell opened up. And the prime used is this prime right here. And again, this is publicly available information. The National Institute for Standards and Technology has published this information for everyone to use with cryptography. Okay, so the prime used is 2 to the 256 minus 2 to the 224 plus 2 to the 192 plus 2 to the 96 minus 1. Okay, so that's a big prime number. However, notice the biggest power of 2 here is 256, right? So at the biggest, this is a 256-bit prime number. Take a second and try to recall the size of prime numbers used with RSA, and you'll remember that the keys were 2048-bit, which means that the individual primes used were at roughly 1024-bit primes. Okay, so this prime here, in relation to the prime numbers used with RSA, is much, much, much smaller. Okay. But we get, again, most modern websites are using elliptic curve cryptography, and we get about the same security with much smaller prime numbers, which is why a lot of websites are using elliptic curve cryptography. There's less overhead as far as generating huge prime numbers. There's a trade-off there with, like, the operations are tougher to do on elliptic curves, but most web developers have agreed that trade-off is a good one, because I can program a computer to do those operations, but computers can store huge numbers, but they only have so much memory, right? So that's why this trade-off is done. The generator is also uses huge numbers. So let me go show you these numbers that I'm not showing you. Let me show you those numbers now. So I've got this Sage cell right here. So here's the elliptic curve. So again, we're using this prime number, 2 to the 256 minus 2 to the 224 plus 2 to the 192 plus 2 to the 96 minus 1. And then we're using the elliptic curve where A is minus 3 and B is this thing. I don't even, how many commas are there? This is a pretty big number going on here. But again, in relation to the numbers going on with, say, RSA, is actually relatively small. Okay, so there's that number right there, that B number. You can see why I didn't put it in the notes. I actually tried and it flowed over the edge of the page. Okay, and here are the coordinates used for the primitive root, if you will, for the generator of this elliptic curve. Okay, x1 is that, y1 is that. Okay, so if I print, I don't know why I would, but I could print P, there you go. There's my generator of this. Oh no. Oh no. Oh no. Oh, I lost everything. That was my generator of my elliptic curve. Okay. I'm going to pause and get that back. All right, I got those parameters back. So there's our generator of this elliptic curve over this finite field. And so if Alice and Bob want to do this Diffie-Hellman key exchange again, Alice can again come up with any secret key that she wants. Let's say she wants to use the secret key 10. Bob wants to use the secret key 915. Okay. Then Alice computes the point Q, which is 10 times P. Bob computes the point R, which is B times P. Let me do A times P there. And then the shared secret key, which I'll call S, should be, from Bob's perspective, B times Q. And then so I'll call this SB for shared secret key from Bob's perspective. SA for shared secret key from Alice's perspective should be A times R. Okay, so let's print SB. Where's that comma? I have a comma there. There we go. 2 to plus 2. There we go. Sorry, everybody. There we go. So there's the shared secret key from from Bob's perspective, and here's the shared secret key from Alice's perspective. And you can see, because they're printed out right on top of each other, that they get the same shared secret key. And again, these are numbers that are really used with modern cryptography. Now, Alice and Bob shouldn't choose such small numbers. They should choose numbers ideally at random between 0 and roughly P. So that's how they can generate a shared secret key using a commonly agreed upon safe elliptic curve. Okay. There's another elliptic curve that is considered pretty safe, and that's curve 25519, and that uses the prime number 2 to the 255 minus 19. That's the prime number that's used. The elliptic curve, that one is, it actually doesn't have the form that we're used to, the y squared equals x cubed minus ax plus b. That one uses what's known as the Montgomery form, I believe, which is y squared equals x cubed minus ax squared plus bx, or plus ax squared plus bx. You can get from the Montgomery form to this form by just a change of variable. But because it uses that form, I didn't want to use it for this example. But if anyone's interested in it, that curve is actually considered a little bit safer than this curve. So curve 25519 is something that you can look up to see another curve that's used in modern cryptography. Okay, so curve 25519 is another one you can look up. Okay, and in general, there's a bunch of curves that you can go and look up. There's let me show you the actual website that I got these parameters from. So the website is this website, safecurves.cr.yp.to, which just collects a bunch of different elliptic curves. So here's a bunch of elliptic curves that are used in modern cryptography. We've got our curve 25519 right there, which is again 2 to the 255 minus 19. That's the prime that's used. You can see NIST 256, and there's that prime number that we mentioned. We've got the equations for these things. So curve 25519, if I zoom in a little bit, curve 25519, again, it uses a Montgomery form, which looks a little bit different. But so it actually leads to a much nicer looking equation than the one we used for NIST P256, right? Here's that equation that we used. Oops. Here's the curve for curve 25519. Okay, and you can see a bunch of different elliptic curves given here. We've got this SECP 256K1 uses this really nice elliptic curve. Let's go look at the prime that's used there. The prime SECP 256K1. There's the prime that's used with that one. And then you can also look up the base points that are used on all these things. So curve 25519, the base points are, the x coordinate is 9, the y coordinate is that thing. The NIST P256, we see those numbers that we used in that example. That SECP 256K1, which had really nice parameters up until this point, has these big numbers for the base point, and so on, right? So you can look at all these base points as well, which is pretty cool. All right, so that is the idea behind Diffie-Hellman, but with elliptic curve cryptography. It's the exact same thing as for any cyclic group, right? The discrete logarithm problem is difficult to solve in some groups, not so difficult in others, but in this group in particular, it's incredibly difficult to solve. And so we use that for modern cryptography purposes to get to a shared secret key between two parties that want to communicate. Okay. So next time we'll talk about Elgamal, which is built on the Diffie-Hellman key exchange using this elliptic curve cryptography idea. And that'll be it. That'll be it for the semester. So thank you all for your attention. If you have any questions, feel free to email me or talk to Dr. Hassinian during class. Okay. Thank you all, and I'll see you for the last video next time.